Imagine randomly marking a point inside a circle. What's the probability that this point is closer to the center than to the circumference? The answer lies in dividing the circle into regions. By halving the radius and constructing a smaller circle inside, any point within this smaller circle is closer to the center. The probability is simply the ratio of the smaller circle's area to the larger circle's area. The math is straightforward. The area of the larger circle is pi times x squared, and the smaller circle with radius x over 2 has an area of pi times x squared over 4. So the probability of being closer to the center is p for center equals the area of the smaller circle divided by the area of the larger circle equals pi times x squared over 4 divided by pi times x squared equals 1 over 4. Therefore, the probability of being closer to the center is 1 over 4, and the probability of being closer to the circumference is 3 over 4. Now, what if we extended this idea to regular polygons like triangles or squares? Could the probability of a point being closer to the centroid reveal hidden spatial patterns? Now let's find probability for regular polygons. For this demonstration, let's consider an equilateral triangle. From the center of the triangle, a perpendicular line is drawn to the nearest side, dividing it into two equal parts. Using half this length as the radius, we draw a circle. Any point inside this circle is closer to the center than the perimeter. You might wonder why we opt for a circle inside the polygon rather than an inscribed polygon. In fact, both configurations are essential for assessing the maximum area near the center of the polygon. To make the inner inscribed polygon, we begin by identifying points equidistant from both the center and two sides at each of the triangle's vertices. These points create a Y-junction, which serves as the framework for constructing an inner polygon, effectively a scaled-down version of the original triangle. To optimize coverage between the maximum points on the inner circle and the inner triangle, we employ a rouleau-like structure. This structure is formed by drawing arcs that pass through three critical points: a corner of the inner triangle, a point on the inner circle, and other corner of the inner triangle. These arcs minimize gaps near the center, forming a shape reminiscent of a rouleau triangle and maximizing coverage within the polygonal confines. Check out my next video on the transformation of a regular polygon into a circle and its associated probabilities. For a comprehensive derivation and further details, please refer to my research paper.